I'm here to introduce Dr. Jenna Samra and Dr. DeLuca, and they're going to tell you about their observations of total solar eclipses. So this is a really nice picture of a total solar eclipse. You guys probably know that a solar eclipse happens when the moon comes in front of the sun, and it happens because of this crazy coincidence that the moon covers the same apparent angular size in the sky as the sun. So it covers the bright surface of the sun, and you can see the corona. You can see all of this structure. There we go. You can see all this structure out into the upper atmosphere of the sun. So this is a picture of the 2017 total solar eclipse, not taken by me, taken by a team out of, I think, University of Hawaii, and Miloslav Druckmuller has done the processing on this. It looks really nice. So 2017 was the eclipse that went across the US. And did anybody see the eclipse? Yeah, lots of people. Anybody? Were you guys all in totality? Did you see the? Oh yeah, where were it? Where'd you guys go? Nebraska. All over. So we had people all along the path here. I was up here in Oregon, and that was pretty cool. So here's me and my husband. We were camping in Oregon, and we got to see the eclipse. And it was awesome. And we said, we're going to take one picture of the eclipse, and then we're just going to look at the sky. That's what we're going to do. All right. So there's our one picture. Okay. It's not as good as the first one, right? But that's our one picture. And I'm a solar astrophysicist here at the Center for Astrophysics. And so people would always ask me, so are you going to take any scientific measurements during the eclipse? And this was basically my answer, which is, no, I will be looking at the sky going, oh my gosh, this is amazing, right? So I was out in the desert, kind of hanging out and going, oh my gosh, this is amazing. And those of you that have seen a total eclipse know that's true. If you haven't seen one, 2024, Northern New England, go check it out. You should do it. It's great. So while I was doing that, while I was out in Oregon and you guys were in Nebraska and Illinois and all those other places, my colleagues here were here. They were in this airplane. And while I was looking at the sky and going, oh my gosh, this is amazing, they were doing science. So this is Jenna Samra doing science. And Jenna got her PhD from Harvard in the Applied Physics Department in 2018, and her dissertation was based on the development of this instrument on this airplane to look at the eclipse called AIR-Spec. And now she works at the CFA developing instrumentation for observing the sun. But before she went to grad school, she had a life, and she was an electrical engineer. And she worked at MIT Lincoln Labs, developing sensors for environmental monitoring. And she's brought some of that experience to the CFA as well, in that she is developing an instrument called methane air, which is a instrument that monitors methane in the Earth's atmosphere. So that's Jenna. Oops, there we go. We also have Ed. That's Ed. Actually, I think this is the back of Jenna's head right here. But this is Ed. And Ed DeLuca You wouldn't really know it from this picture, but he started out his career as a solar dynamo theorist and modeler. And he did his dissertation on that in the University of Colorado. Then he moved on to have jobs at the University of Hawaii and the University of Chicago before coming to the CFA in 1993, where he's been working increasingly on projects that mean he ends up wearing a yellow vest, staring at gas coming out of machinery, meaning instrumentation projects. So he's the PI of the X-ray telescope on the International Hinode mission. He's been working on the AIR-Spec telescopes with Jenna and a variety of other instrumentation projects. So while I was out in the desert oohing and awing at the sun, these guys were working hard. But it turns out they did get a little bit of time to look at the sun. So let's welcome Dr. Jenna Samra and Dr. Ed DeLuca.
Thanks.
Thanks.
Is my mic on? Yeah. Okay, so Ed and I are going to be doing a presentation today. We're going to be tag teaming. And we'll talk about chasing the total solar eclipse from the airplane at over 40,000 feet. We're going to start out with the specifics of that project, and then Ed's going to talk more generally about why we want to study the sun. So we're sort of inverting the typical presentation here. So Kathy covered this pretty well, but I just wanted to show you the paths of the two total solar eclipses that AIR-Spec observed. So this one is the one that many of you saw. It covered the whole U.S., west to east coast. And the 2019 eclipse, which was the next total solar eclipse after 2017, just barely touched land over South America. Most of it was over the South Pacific Ocean. And actually the best place to observe, the longest duration of totality, was right here, just north of Easter Island. And so, as Kathy said, we were in an airplane. We made a pretty unique observation in that sense. And so here's where we were. So this is the Gulfstream 5 airplane owned by the National Science Foundation. We observed over Kentucky during 2017, and over the middle of the Pacific. It took us 6 hours to get there in 2019. And so I'll tell you a bit about both observations. I'll show you some of the data and talk about some of the instrument development, what our instrument does. But before that, so Kathy talked about this in words, but this is the geometry behind a total solar eclipse, right? So you have the sun, as Kathy said, the moon is the same size angularly in the sky, and so during times when the moon appears a bit bigger than the sun, we have a total solar eclipse, and the sun is completely blocked out, and there's a point on Earth where it's in the moon's shadow, and we can actually see the corona, the outer atmosphere of the sun. So here's a sequence that just shows you kind of going from partial to total, and then back to partial again. So here we can see the moon just starting to cover the sun, and here it's fully covered. This is totality, and then it gets uncovered again. And the photosphere here, the photosphere is the part of the layer of the sun that we see every day. This is about 1 million times brighter than this here. They look the same on the scale. But so the total solar eclipse gives us a really a great opportunity to study the corona, and that's exactly what we did. So I think this might be the same picture, or a very similar picture of the 2017 eclipse that Kathy showed. It's been highly processed to show all of this structure, and she pointed that out. And so the structure is pretty interesting. It's actually caused by the magnetic field of the corona. And so you can see that, so in the corona it's very hot. The gas is ionized, so there are free electrons and there are ions. And so the particles actually, because they're not neutral, they actually interact with the magnetic field and follow the field lines. And so that's why you can see that the light also follows the field lines here. So this is a model of the magnetic field during the eclipse that was made by Predictive Science. And you can see it matches really well the observation. This is actually an observation that's been processed, but it's a picture. So clearly the magnetic field is important. It provides the underlying structure for the corona. Also, we can see here that it also is the force, the underlying, supplies the energy for solar activity. So here, from left to right, this is a solar flare. So it's energy being released as light. You can see here the magnetic field lines that are kind of traced out here by the plasma after a flare. And then in addition to producing light, magnetic eruptions can actually send material off of the sun, so plasma and magnetic field. And so that's shown in these last two. And so the magnetic field, as the sun rotates, gets kind of twisted up. Ed will talk much more about this. It can reconnect to a lower energy configuration, and that extra energy is released and produces phenomena like these. So some of these can be Earth effective, like in particular the coronal mass ejection here, if it were pointed the right direction, would be potentially Earth effective, and Earth's magnetic field protects us from that, and Ed will talk more about that. But there's reasons that we want to study this, right? And so in order to get at the heart of this, we need to be able to measure the magnetic field of the corona, and that's in order to predict eruptions, in order to understand the structure, that's a difficult thing to do. And so one of the reasons it's difficult is because the magnetic field is very weak. Also, we're here on Earth, so how do we do this? We're not at the corona. Well, not our instrument, at least. And so what we can do is we can measure the light that's emitted by the corona. So the way this works, this will probably be the most technical slide. So if you reach back to your physics or chemistry classes in early college or late high school, maybe, this is an example. We could picture this as a hydrogen atom. And its electron can occupy different energy states. They're discrete, so it can either occupy this one or this one. If it drops down from an upper one to a lower one, it loses energy. That energy is released as light of a particular color. And depending on the transition here, the colors are different. So you can have, in the visible, you can have violet, red, blue, etc. If this happens in the presence of a magnetic field, you won't just get one wavelength at each of these lines. We call these lines, emission lines. I'll use that word a lot. You actually get a splitting. So you get three or more very close to each other. And the amount of the splitting is proportional to the magnetic field. So by measuring the splitting, we can actually infer what the magnetic field strength must have been. And so this is a way that we can remotely measure the magnetic field from Earth. So that brings me to our instrument, which does not measure magnetic field. So our instrument is called AIR-Spec. It's the Airborne Infrared Spectrometer. It is doing the step before measuring magnetic field, and it's just measuring the emission lines. So it's not able to see the splitting. It can't resolve it, although the splitting is happening. So it's just characterizing the lines, and eventually a future instrument will be based on our results to actually measure the magnetic field. So again, this is the hydrogen example. So this is an example of the emission line. You can see it in colors here. This is kind of similar to the spectrum. If you've ever looked at like a hydrogen lamp or something like that, you might see those discrete lines, as opposed to if you looked at the sun dispersed, you would see a continuous spectrum. So if you look at just the intensity of each of these lines versus wavelength, you see something like this. So this is a simplified version of some of what I'll show you later on in the talk. So this is our instrument that we built. It's on the airplane, as Kathy said. You can see it. I have some better pictures of where it's located, but you can see it here. It's on the left side of the plane. The front of the plane is up here. The cockpit's up here. The back is back here. And right now, the instrument is being cooled, or at least at the time that this picture was taken, the instrument was being cooled with liquid nitrogen, which is the reason for the water vapor and the nitrogen coming out. Okay, so I'm going to go through the name. We named our instrument in kind of a very obvious way. And actually, the name says everything we need to know about it. So I'm going to go through one word at a time. So it's airborne. It flies on the NSF Gulfstream 5. The Gulfstream 5 is usually a corporate jet, and this one has these special portholes with optical quality glass. We don't look out the plastic window. That's a question that a lot of people ask. And so this one's been outfitted for research, and so it can get up to something like 50,000 feet, depending on the weight. We flew at 43,000 and 47,000 in the two eclipses. This is the Gulfstream 5 where we were based in 2019 in Lima. This is another picture of our instrument on the Gulfstream 5. Now the back of the plane is in this corner of the picture. And one of the challenges of putting your instrument on an airplane is that you have to build it to be modular, because you can't fit this whole optical bench through the door. So this is a picture of us actually installing, or the crew, the airplane crew installing. So this was kind of a scary thing to watch when my thesis was depending on on the success of this instrument. But it got much easier after that. But they did a great job, so there were no worries. So why go through the trouble of being airborne, right? When you can observe from the ground, and you've seen these beautiful pictures that ground-based observers take of the eclipse. Well, that's because we're looking in the infrared. So infrared light, it's a longer wavelength than visible. Visible is what your eyes see. It's heat. So the way that you've probably experienced infrared light is as heat. And it turns out that the atmosphere, although it transmits the visible all the way to the ground, it doesn't transmit all of the infrared light. There are some places where it does, not everywhere. So to actually see the emission lines that we were looking for, we had to be up above the atmosphere. And that's why we went through all the trouble of being in an airplane. I'll talk about why that was so much trouble a little bit later on. So one of the other big issues about the infrared, in addition to being in the plane, is that it's heat, right? So the light from the corona is really faint, and the heat from the instrument could completely swamp it out if we didn't cool the instrument. So here we're pouring liquid nitrogen into the instrument. It's venting out here, and we cooled all the optics inside here. I'll show you to about minus 200 degrees Fahrenheit or below. And that was just so that the instrument itself wouldn't be so hot, wouldn't be shining that bright light onto our camera, so that we could actually see the corona. Okay, so finally, it's a spectrometer. What does that mean? So typically, when you look at an image, you see, this is going to sound pretty obvious, but you have two dimensions to the image, and they're both distance or spatial dimensions. But we know that this white light image is actually made up of all the colors of the rainbow. And so there's actually a third dimension to this image that's hidden in here. And so if we could spread out that third dimension, we actually have a three-dimensional cube here, where this is wavelength, and then you have your two spatial dimensions. We only have a two-dimensional camera, though, so we're going to have to collapse this data along one of the spatial dimensions in order to observe the spectrum. So what we do, instead of taking a cut like you normally would, here, we take a slice through the wavelength, so we get wavelength on one axis, and we get distance on the other. So you can see here, this black thing is the limb of the moon. It's the moon, the part that's overlapping the moon, and then here you have color. And so that's what our data looks like. This is false color because it's in the infrared, so we don't actually see colors. But this just to give you an idea. All right, so this is our instrument. We have, if we go from the light path, light goes in here. It hits an initial mirror and then goes through a telescope and into our spectrometer. So each component is here for a reason. We have the steerable mirror, the first thing it hits. This is actually electronically controlled, so it takes out the motion of the plane so that we can keep the image of the sun nice and stable in the camera. We have the telescope, which focuses light, just like everybody's familiar with. We have the spectrometer, which actually spreads out the light. That's what actually gives us the wavelengths in the way that I showed you before. And we have a couple of cameras. We have the context camera, which just takes these white light images like you're used to, and we have the IR camera, which takes these spectral images. And then, because we're on an airplane, we have a couple of other things. We have a gyroscope, which tells the mirror how to turn. It measures what the airplane is doing, and tells the mirror how to correct for it. And because we're in the infrared, we have to cool our optics, as I mentioned, with liquid nitrogen, because they're cooled to minus 200 degrees Fahrenheit, we can't have them condensing, right? So they can't be out in the atmosphere. They have to be in an evacuated chamber. So they're in a vacuum chamber. All the air is pulled out of this chamber, and that allows us to cool the instrument without condensation. All right, so this was one of our biggest challenges. It was stabilizing the image on the airplane. So this slide also shows a bit about the difference between our 2017 and 2019 observations, and kind of the improvements that you can do if you when you're working on the project for the second time. So we didn't fly this case. This is if we hadn't stabilized at all, we wouldn't have been able to point to one location on the sun. The sun would have just been moving throughout our field of view. Sometimes it's completely out of the field of view, and this is happening as the airplane kind of rolls. It's the kind of motion that causes this, because this is such a tiny angle. The sun itself is only half a degree across. It's not even a motion that you would feel if you're in the airplane. You think you're totally steady, but you look at the image of the sun and it's going all over the place. So in 2017, we measured the airplane's rotation, and we attempted to correct for it with our mirror, and we did a pretty good job. Sometimes we even did better than what this video shows. And so we were able to keep this dark line here is the entrance to the spectrometer. So the light that gets through this dark line is the science light that we care about. All the rest of it is just our context image. So we want to keep this dark line in one spot on the sun. And we were able to do a much better job than if we hadn't done anything. In 2019, we added something. We actually tracked the edge of the sun in the image. And so that gave us a bit, but actually significantly better performance, especially in allowing us to hold one position on the sun. So you can see an example here. 2017, we had to, the eclipse wasn't going to wait. We got up there. Our system worked, but it wasn't perfect. 2019, we made it better, and then next one we're gonna do even better. The other big challenge, I mentioned that we had to cool the instrument, so you saw this video already. The reason that it's cooled, so if anybody's ever taken a photograph in really low light, you know that it can look grainy or noisy, right? So the background that's produced by the instrument, if you didn't cool it at all, actually produces that kind of graininess, and the coronal light is very faint compared to it. So if we hadn't cooled, you would see something like this. I mean, this is false data. We didn't actually do this, but this level of noise is about what you would see. You can't see any of the structure in the corona. All you see is that the color is changing because of the spectrometer. So in 2017, we cooled the instrument. Not only did we have to cool it, but we had to shield the camera from light leaks. We did that kind of as well as we could. And you can see it was still pretty noisy. This is for about a 30-second exposure time as well. These aren't quick exposure times. In 2017, we did get good data. You can see some of the structure here that's in the corona, or actually in the coronal light. And so this was enough to tell us that we were on the right track, and it was worth flying another mission. And then in 2019. We actually did a much better job of shielding the camera from the heat that was coming from the instrument, and of cooling the instrument. And so we got a much even better, about 4 times better noise performance. All right, so I'm going to talk about our eclipse observation. So this is a view of Ed and I in the airplane. We weren't the only ones there. We had 2 other people from Smithsonian. That one of them was timing everything with the pilots, and also calling out the time for us to go from one position to another. The other one was moving the optical bench up here. Oops. And doing some of the alignment on the pre-eclipse alignment, pre-totality alignment. During totality, everybody except Ed and I were kind of just staring out the window that was right here, because there was nothing else to do, and they could see the eclipse over my head. So there was also, we had a couple of crew members. We had 2 pilots, a mechanic, and 2 program managers that were on the plane as well, that they work at NCAR. So this instrument is not, it takes a lot of people to run it. It's not really automated. So during the eclipse, I just wanted to give you kind of a feel for what it looked like. So I'm looking at the screen, and I'm pointing to different locations on the sun. I can only see the context image. Ed is looking at the IR data to see if we see any of the emission lines that we're looking for. So one of the things that we weren't sure about was whether we could track the edge of the moon as well as we could track the edge of the sun. We had done a whole lot of practice on the photosphere, the solar photosphere with its nice sharp edge, and the moon is not nearly as nice of an edge. So this is right after totality started. I'll show you just a quick clip of, this is me in the airplane. It's really dark because it was dark outside. And this is what's on my screen just blown up. So we're excited because I was able to bring the sun to the center.
I can barely see my screen.
And then we go to position 1.
Position 1.
And so what we mean by position 1 is the slit. Remember, all the light that goes through this dark line is the light that we care about. It's in this particular part of the corona. So during the rest of the 9-minute observation, we moved around to different parts of the corona. And this is basically, the white lines show you where we actually got data. And this is a processed image of our context camera. So this is what our spectral data looked like. You've seen this. You know how it was produced. But if you actually want to see what the spectrum looks like in the way that we typically look at it, just imagine taking kind of the top row up here where it's bright and now plotting the intensity across that row. So you're not worried about this spatial dimension anymore. You're just plotting intensity, and the color doesn't have any meaning. Color just goes left to right. So then you would get something like this. So you can see that this bright line corresponds to this sharp peak here. And there's a whole lot of absorption lines that go down. And so what that is actually, this is absorption from Earth's atmosphere. This is emission from the solar corona. This line is what we're looking for. The absorption is kind of in our way, and we have to model it out as we go on with the data processing. So this is just a more full picture of the data that we got. We had 2 channels, so this is the other channel. We had a really nice bright line in this channel, and then we had 2 others, and we actually saw all 4. We were looking for 4. We saw all 4. In 2017, we were looking for 5, and we did see all 5. They were slightly different. Some of them were the same. So it was a successful mission. We got about 7 minutes of data. And so the reason that we want to see these, I told you about measuring magnetic field. I told you that we can't measure magnetic field. We're paving the way for a future instrument to do that, and that's important. The other thing that we can do using the intensity of these lines is look at the temperature and the density of the corona. And we can do that already with the instrument that we have. So I'll hand it over to Ed, and he's going to talk about, more generally, the sun, studying the corona.
Okay, thank you, Jenna. So let me just on this slide, this is part of the project that we're funded by the National Science Foundation, and part of their interest in funding eclipses is the science, and we're going to discuss the science. We've talked about the instrument developing capability. So this was the first time that this airplane actually had a stabilized pointing imaging capability was in 2017. That was part of our program to develop the ability to image from that plane. The plane had used pointed at the sun, but it didn't really care whether it was stabilized or not. But if you want to take images, if you want to do the science that we're doing or other certain atmospheric science, having a stabilized platform is really important. The methane air program that Kathy referred to, that Jenna's working on as well, relies on having stabilized imaging. So that's part of the program is developing technology. And part of the program is also outreach. The NSF has a strong commitment to education, a strong commitment to public outreach, and bringing science to other people. Since we were stationed in Lima, Peru, which was kind of the airport closest to the maximum of Eclipse, so we had the shortest distance, even though it was like a 6-hour flight. But Lima, Peru is a city of 8 million people, which I kind of hadn't realized on my ignorance of cultures. So it's really large, it's really crowded, it's really hard to get around in. And once we committed to going to Lima, Peru, NSF and the NCAR people who are used to bringing airplanes outside the country went into action and interacted with the U.S. consulate in Lima, Peru. They provided us with translators, with facilitators, with a location on the airport, part of the military base, air base in Peru that the U.S. has access to, created all of the permissions to fly in and out at specific times, as opposed to the day of the eclipse. The eclipse happens when it happens, and so you can't change it. Like, oh, we got a 5-minute delay half-hour delay on the tarmac. It happens, right? So you have to be there. So, conveying that information to the air traffic control people in Spanish appropriately with proper respect is not something that I could possibly ever do, right? So there are people who did this, and there's in fact vast numbers of people. And so the project was really a lot larger than I think we had any notion of when we proposed to fly this eclipse in Peru. Part of our planned outreach was we brought in a college undergraduate who was a native speaker of Spanish. She's from Puerto Rico. She worked with us in the summer to come up to speed on our project. She worked with Spanish language native speakers at the CFA, practicing how do you actually talk technical Spanish, because it's not actually learned, right? I mean, the science, the language of science is almost dominantly in English. And so coming up to speed in how do you explain what we're doing in appropriate Spanish was really hard. She relied on some of her relatives, practiced her talk here, there, and over the phone with people in Puerto Rico. The accents are different in different parts of South American countries, of course. And so she and Chad Madsen, who's a scientist here, was working on the science aspect with her and bringing her up to speed on why we're doing this. He has a little bit of a Spanish background. And they gave this presentation to college students in Lima who were visiting Lima from a small mountain mining community outside of Lima. They'd come into Lima for a visit. This presentation was arranged along with their visit, and it was really a unique experience for them to be able to understand what is a state-of-the-art science investigation in the language that they could understand. That none of them had English language ability, and actually ask questions and interact. So this was an incredibly successful part of the program. Here we have professors from the university, as well as scientists. This is from the U.S. consulate, and members of the Peruvian equivalent of the National Science Foundation visiting the plane, and we gave them a tour. You can tell it's winter in Lima. It's an equatorial place, but so winter in Lima for the people from the U.S. we're in t-shirts. Winter in Lima for the locals, they're in down vests. So it's like you can tell who's local and who's not. It's like they felt it was really cold, and we're like, well, it's pretty comfortable for us. So that's an aspect of this project that I think is worth understanding, and it was something I had really should have appreciated, but didn't really appreciate that much before we got deeply involved in this. So, why study the sun? A couple of reasons, right? From this institution's point of view, a lot of the time I'm talking about the sun is an astrophysical object, right? It is the astrophysical object that we can actually observe spatially, we can observe temporally, we can observe spectrally. It's really bright compared to everything else, and we have a lot of technology that we can attack and look at the sun. So the things that and our fundamental belief in physics is the physical laws that apply here apply everywhere else in the universe, right? If that's not true, then there's big problems, right? So that has to be true. Otherwise, we don't know what we're doing. But as far as we can tell, the physical laws that apply here apply everywhere else. So looking at the sun is a useful exercise. And NASA, our thing was funded by NSF, but NASA is a huge player in this, and we're supported a lot by NASA. And they have a fleet of spacecraft that look at the sun, look at the Earth's magnetosphere, look at the Earth's ionosphere, the interactions between the sun, the Earth's magnetosphere, the heliosphere that's in between. This is not empty space. There's a gas in here that transmits the energy from the sun through interactions of the solar wind on the Earth's magnetosphere. So these are representing magnetic field lines that originate in the core of the Earth, protect the Earth from the high-speed solar streams, and form out into the tail. And so all of this fleet of instruments is geared towards understanding how magnetic fields that are storing energy on the sun and releasing energy on the sun, plasma, hot gas being carried with them, how that follows through the whole heliosphere out into interplanetary space. So the sun and the heliosphere consist of plasma, and plasma is the most common form of matter in the universe, right? And so it's a gas, right? So as Jenna mentioned, back to your atomic physics, the nuclei and electrons, right? But from our point of view, we're not going to get into anything more subtle than that. And if the gas is heated, electrons leave. So you have free electrons and ions, which are atoms that have lost some of their electrons and no longer neutral. When you have that situation, the gas is highly, highly conducting. Highly conducting gas is able to contain magnetic fields, generate magnetic fields. Magnetic fields distort the gas distorts the magnetic fields depending on who's pushing on whom, right? The surface of the sun, in the interior of the sun, the highly conducting gas is twisting the magnetic fields and doing what it wants with them, generating the magnetic fields in the interior. The sun rotates, it convects, that generates magnetic fields. In the outer atmosphere, the situation is reversed. The magnetic fields dominate, the plasma goes along for the ride, and the energy is stored in the magnetic fields and then released and accelerates the plasma, and can also accelerate it thermally and can also create high energy particles. Right? And so, yes, as I mentioned, magnetic fields play a critical role, and the conditions of matter depend on what we see. So this is one of my very favorite movies, and sort of explanations as to why is it that I'm in solar physics. Right? If you look at this movie, gas is illuminated, and what you're seeing, bright things are dense things. It's all pretty much the same temperature because it's a narrow emission line. The sun is rotating. This is about a 2.5 month time period over the course of this movie. The sun rotates 28 days of the equator. And the structure is controlled by the magnetic fields that originate in the surface and thread into the outer atmosphere. So there's dynamic things. These are called active regions. The dark stuff here is filaments, so it's cool, dense plasma that's blocking the light from below. Some of the dark things at the poles are absence of strong magnetic fields, so you can see down to the surface. There's the edge of the sun, right? So in these emission lines of iron, you can see the entire coronal down to the surface of the sun because the photosphere is not emitting in this wavelength, right? There's a very bright photosphere under here, but it's not emitting at this 17.4 nanometer wavelength. So we built telescopes such that we can see it here, and you can see the entire corona. And the globe, there's log scale structure, there's small scale structure. The characteristic of magnetic fields is that it has what we would call a long correlation length. In one direction, things are fairly smooth, and you go across the fields, things change very rapidly, right? And that kind of gives you a sense of how currents are stored in the magnetic fields, the structuring, and the dynamics. And all of this is stuff that we need to understand in more detail. And this is going on everywhere in the universe. There are magnetic fields, there's plasma, there's rotation, there's energy storage everywhere in the universe. And most of it is vastly more energetic than the sun. Fortunately for us, because we are here because the sun is not a terribly active star in some ways. Space weather, right? We are here. Existential questions, right? So the photosphere of the sun is what, for all of humankind, is what we see. We know the sun is, intuitively understand that the sun is responsible for life on Earth. And, it's in our genetics. The sun is, it's there. It creates all the energy. It creates the ability for things to grow, for animals to grow, all that stuff, right? So understanding, so there's a natural concern. It's like, is it going to be there tomorrow? Is it going to be there, for my children, my grandchildren? And of course the answer is yes. So this is not a problem. Existential question number one, the sun is, this is in billions of years, right? So 4.5 billion years. Billion years is a long time. And the sun is kind of gradually changing over the billion-year time frame. This is not what's going to do us in, right? The large-scale life cycle of the sun, that's not our problem. Okay. We like XKCD. Yes, so there's a connected system between the sun and the Earth, but it just from the white light, it works, and we're happy. Now, for technical societies where you've got, currents and satellites and electronic systems, and you want to talk to people, use your GPS, then other things come into mind. And so existential question number two is, what happens? The sun is a variable star. We saw some of the explosions in the sun before. And are those issues that we really, really should be concerned about? And the answer is, yeah, probably we should. So, sunspots, right? Sunspots are manifestations of the magnetic field poking through the surface. So when you have very strong magnetic fields that are generated in the core of the sun, and they erupt through the surface, because magnetic fields in the interior are buoyant, they appear dark. And they appear dark because they're cooler than the surrounding, and they're cooler than the surrounding because here the magnetic fields are sufficiently strong that they inhibit the motion, convective turnover motion of the sun. So if you look at this picture here, a close-up of the photosphere, these little items here, this is probably the size of Texas, right? More or less, right? So that's a convective cell and a granulation cell in the photosphere. And when the fields are weak, that's how energy is released. The most recent, the topmost level of the convective layer looks like that. When you have strong fields, that is suppressed, and so you are not pulling heat up from the surface. It's cool. The outside is still cooling. So the temperature here is lower than the temperature there, and that's why it appears dark. And these filamentary structures are areas of sort of intermediate magnetic field strength that are extending between the sunspot, this is penumbra, and the granulation. All right, so they're sunspots. And the magnetic nature of the sunspots was measured by Hale in 1918 using the Zeeman effect. But the observation of sunspots had gone back to Galileo, right? So, when you start, as soon as you put a telescope on the sun, and probably, you should really, Galileo didn't do this, but, if you do it in projection, you're not unlikely to go blind. But suddenly you see sunspots, and then you start recording them, and then over years that, the number of sunspots comes and goes, right? And so, Galileo was over here, and people, were very excited about these dark, varying features on the sun. And then there was this period in which there were very few sunspots, and there are, recordings of people who observed the sun regularly with telescopes and said, I have seen a sunspot for the first time in my life, right? They had known about Galileo's observations, but had really never seen them themselves. So there was something strange going on, and then the cycle picked up again. Different time scale here, but so the number of spots varies, sort of quasi-periodically, the amplitude changes. The direction of the spots, they tend to form at high latitude. This is latitude, so the poles, North Pole, South Pole, equators here. So this is about, plus 40 degrees, something like that. And they start at high latitude and they propagate to degrees. So these are just characteristics of how the sunspots behave. We're not going to go into the dynamo theory of the sun, but we could if that's required. Right, so the sunspots then erupt through the surface, and that's where we come in. So here's another view. Sun is rotating. This is from a telescope that was built here in Cambridge, the Atmospheric Imaging Assembly. And we did that. And it's still flying on the Solar Dynamics Observatory. And this is a strange scaling. So there's one color scale used on the disk, and then a radial filter on the outside so you can pull out the very faint structures on the outside. So bright things here and bright things there are very different in brightness. But you're seeing, things erupting. Okay, so that's, and when those things that are erupting hit the Earth, there's a model of, here's the sun, here's the Earth's magnetosphere, and the interactions can be dramatic. These are simulations of sort of how magnetic structures evolve through the interplanetary space and hit magnetospheres. The point is that even though these things appear localized, as soon as they're in the interplanetary space, they expand dramatically, and so the cross section of them can become quite large, and we're going to see an impact of that. Now, final XKCD cartoon of the night. Like this, we feel self-important, right? So, what happens, right? It's archaeology. We don't so much care. Maybe the bees go away. That's really a problem, right? Astronomer studies the sun, and if the overtake tag is, it's like, well, we like to be called solar physicists. It's like, what's wrong with the sun, right? So that's us. The sun could kill you, more at 11. And so, right, and in fact, there are studies about how the sun could kill you, and there's a National Space Weather Action Plan to try to, mitigate these things. So we're going to talk a little bit about the Carrington event. This is, there was a movie, I didn't see it, but I think it's probably terrible. It's one of the standard disaster films that says, what happens when the Carrington event happens now. But, so in 1859, this English astronomer was observing the sun with his naked eye, and he was drawing pictures of the sunspots, and he noticed this white light flare on the sun, which is, in order for the sun flares to emit invisible light, they have to be really pretty substantial. 2 days later, aurora is seen down to the equator. And telegraph operators report keys bursting into flames. You could disconnect your telegraph from any power source and still transmit across it. Really interesting, and that was the state-of-the-art technology at the time. And, there was speculation that there was a relationship between this very bright flare and what happened on the Earth, but not really a way of understanding it. 1989, there was a solar superstorm that brought down some of the power grids in Quebec, and there was substantial power outages and transformers destroyed. And destroying transformers is a nasty business because transformers typically are built as requested. They don't because they're like the size of a house. And you don't just have them and build them and store them and put them in the warehouse because there isn't a warehouse. So, so if you want the next one, it's going to take you months to get it. And so, if you start destroying multiple transformers, you're going to be without substantive power for a long period of time. And that, needless to say, causes people concern. So there was this National Research Council, that's what the NRC stands for, report back a decade ago about what would happen. And, $1 to $2 trillion in damage, 3 to 4 years recovery time, real substantive economic dislocation. So here's the detail. This is actually from Carrington's paper that was published in the Royal Journal of the Royal Academy of Sciences. There's a little flare. This is his drawing of the sunspot. And so, this is just generic aurora picture. All right, so now, you say, well, that was way back then. In 2012, there was a Carrington-sized event that was measured by a NASA satellite stereo that was not on the Sun-Earth line. It was off, and was actually, an event that really would have had substantive created substantive damage on the Earth if the Earth had intersected it. And this is what we call a data-driven model of the event. So this is coming out of the plane. This is the top view. Look at the top view first. So the Earth is here. That's stereo. So there was a CME that hit the Earth. That was not a big deal. There's another CME. This is the short one. Oh. Come on. This is not what I... Hello? Did I not test this? Okay. And there's this. This is okay. Do we have the? This is worth looking at. Okay, we will try to find that after at the talk after the talk. But what I will describe it. Let me. This is okay. My bad for not actually seeing if this worked here. So let's go to, come on, play, and so I will describe what's about to happen. Okay, so stereo is here, the sun is there, Earth is there. There was a CME that went out. There's a small CME here. Then there's after this, there's an initial precursor CME that goes this way, and then a very bright one that follows that. And what we believe is going on. So there's the okay. Well, anyway, if you would, yeah. So what happens in these events that make them very geoaffective is the material in the interplanetary space has a frictional effect on keep slowing down this ejection that's happening here, right? So there's material here. This is all gas in the interplanetary space, and it's being pushed out by the CME, and there's behind it there's a vacuum. Now, if I send another one behind it, there's much less friction. So there's the first one. That's the only thing you got.
This is yours, yeah. I don't know what. This is the original that you gave me. I'm not sure.
Okay.
Yeah.
Okay. That's all that we have.
Yeah.
Okay. So after this event occurred, then there's a following substantial CME came out and went through essentially an evacuated region and hit stereo A. And so the point is that these events occur, right? We're now in solar minimum. 2012 was kind of closer to solar maximum, but they're there, and they're something that we need to understand in more detail, and that's one of our motivations. So what happens when solar? What is the sort of the pathways in which of pathways of destruction, if you like? So there are energetic ions that are accelerated in these in the shocks of the coronal mass ejections, and so high energy protons have adverse effect on electronics in satellites, and they can have radiation effects on avionics in the aircraft. They can also change the ionospheric currents, and you end up having GPS signals that are inaccurate, and so your GPS system kind of fails. When you start shaking the magnetic field of the Earth, moving magnetic fields drive electric currents. If I've got electric currents like transmission lines or pipelines, those will generate the magnetic fields will generate currents in there that are not the currents that those systems are designed to have, right? Which is why the transformers say what's going on here, and they give up the ghost. So so generating these adverse currents in the ground system that's induced currents in power systems, and then kind of anything that looks like a wire over long periods, is going to be affected. So it affects pipelines, communications with submarines, all sorts of things. So that's how you get up to $1 trillion in damage. All right, so that's why we're doing it. This is kind of what we do as a group. So we've been in the space instrumentation business for a fair bit. Some rockets, so the early normal incidence rockets, so these are looking at the sun in the EUV, like that image, the movie that I showed you, and the images from AIA are all in the extreme ultraviolet. You need to be outside the Earth's atmosphere for that to work. SWAF is significant to me because it was the program that was briefly funded and essentially, 1993 is really where it started being funded, which corresponds to my arrival here. So the existence of this rocket and SWAF kind of stabilized me in being actually employed at this institution, so that's why it's here. Trace was successful. The next rockets were very successful. They demonstrated the capability. Trace was a great little small explorer. The X-ray telescope on Hinode is a grazing incidence soft X-ray telescope that's still operating. Atmospheric imaging assembly still operating, and the high C rockets are still going on. We built the telescopes for IRIS, which is a UV spectrograph that's looking at the chromosphere. The AIR-Spec we talked about. And this is the follow-on to AIR-Spec that Jenna has proposed to the National Science Foundation, and we found out it was funded this year, which is essentially building a bigger platform and higher throughput so you can get more sensitivity in the focal plane. These are pictures of various. So this is the X-ray telescope on Hinode and people. So this is tall. This is a 3-meter-long telescope. This is substantial. The normal instance telescopes are more compact because they're essentially Cassegrain design. This has mirrors up here, and the light just comes down to the focal plane. So if you need high resolution, you end up with a very long tube. Here we can have some magnification on the secondary. It's on SDO. We also do in situ observations. So we are involved in the analysis of wind data. We didn't build those telescopes. Analysis of observations on crater. We took over, some of the scientists here took over essentially the Discover Faraday Cup observations before it launched and did the calibrations on that. We were deeply involved in the Parker Solar Probe, which has been very successful and is the fastest thing that was ever built, that's ever flown, the closest thing that's ever been to the sun, and it survived its various close approach. It's at 3 orbits now. That was launched just over a year ago, and we have some people involved in IMAP is looking at the outer heliosphere. Future projects. COSY is a space weather instrument. We had some adverse news about that. We wanted to put this on the space station. NASA said, we're going to do something else. So we have to think about where that's ending up. This is a rocket that's a grazing incidence spectrometer, X-ray spectrometer. And then these two are proposals for mid-sized explorers, one in the EUV doing multi-slit spectroscopy and imaging, and the other one hard X-ray spectroscopy and EUV imaging. And Fierce has this lovely logo. So, fundamentals of impulsive energy release in the coronal explorer. Kathy can tell you more about Fierce. IR projects in the lab. So the IR is challenging, as Jenna pointed out, and spectroscopy is one of these. Atomic physics is kind of understood, but you have to doing the calculations is cumbersome, and you need comparisons with actual measurements to motivate the people to actually do the computations that you want them to do, and so. Doing the observations in space and at the airplane is one thing. Doing observations in the lab is another aspect of that. And our institution here has built this machine called an electron beam ion trap that is able to simulate coronal plasma conditions. And so we can take the spectrometer that was flown on the airplane and point it into the lab. And essentially here you're integrating over weeks to build up a signal, right? Not the 30 seconds that we were taking those spectra before. But it's a very stable environment, and we're hopeful that we can actually start. You can put in different gases. You can really sort of pace your way through the infrared region. And these EBIT machines have been used a lot in the soft X-rays and in the EUV, but we would be, I think, the first ones to look at it in the IR, the coronal lines. We're involved with colleagues at National Center for Atmospheric Research on a ground-based coronagraph. So this is actually a telescope that has an artificial moon blocking out the sun, so you can do coronal observations on a daily basis. It's a big telescope, 1.5 meter objective lens, piece of glass, right? Yerkes, this is bigger than Yerkes, right? Not quite as long as Yerkes. I was at Yerkes. Yerkes is a beautiful place. But, Yerkes is a 1 meter piece of glass, and nobody would ever build that telescope again. But it turns out that building coronagraphs with a 1 meter objective is something that makes sense, and we would be involved in if this gets funded in working on the focal plane instruments. We are planning on building a 0.5 meter coronagraph balloon so that we can actually observe the magnetic structures in the corona over periods of days from 100,000 feet. So no atmospheric absorption lines here. We'll have to do our spectral calibration ourselves, right? We're not going to have the Tyrolean lines to take advantage of. But these balloons can stay in orbit and observe the sun continuously over the Antarctica for about 5 days as it gets into a vortex over Antarctica. So that's what we have in mind. We're going to leave you with the next solar eclipse, so you can make your plans now on where you want to be. As Kathy noted and everyone noted, that solar eclipses are great fun and definitely, if you have a chance, something you should try to see. Thank you.
Who has questions? Jenna and Ed are available to take questions if anybody has some. Yeah, right here.
Okay. What are all the physics behind the Fraunhofer lines getting split by the magnetic fields?
Oh, what's the physics behind that?
Yeah.
So it's something called the Zeeman effect. Have you ever heard of that?
No.
So what happens is you have to understand quantum mechanics to really understand it. What happens is you have degenerate, what are called degenerate energy levels. So basically, there's something that differentiates these energy levels, but it's not expressed until you. So because the energy levels are all the same, you see the same wavelength when there's a transition. And then when the magnetic field comes in, those energy levels are no longer degenerate, which meaning they're no longer the same. So they split, and now you see multiple transitions at different wavelengths, but close to the same one. So it has to do with the angular momentum. It's a bit complicated, but that's essentially what it is. The magnetic field is causing something inside the atom to be expressed that wasn't there before. Does that help you?
Yeah.
Or,
I like know a lot about stuff, but I'd never heard about it before. I was like, what?
Yeah, it's actually there's a lot of good information online.
So it's called
ZEEMAN. I can write it down for you later if you want.
Yeah.
I noticed on the video of the sun going around, you can see the coronal, the atmosphere.
Yeah.
From space. Why can't you do the infrared viewing from a satellite in space?
Oh, great question. It's like we planted you. So that's a good question. The answer is very simply, we can and we would love to, but it's a much more expensive mission, and we wanted to prove that there was something there. And so that's why we're sort of stepping. We're starting with a kind of $1.5 million Eclipse mission. That was the first one where we built the instrument, and then then the reflight in 2019, and then the balloon eventually, which is almost space, kind of the next level. And then if we really show that there's a way to do it from space, then we'll have a much better case for a satellite.
One other quick one.
Yeah.
Do you create the fake moon in the balloon telescope?
Yes,
Yes, it would have a
exactly.
coronagraph,
Yes,
yeah.
it's a coronagraph.
Yeah.
Yeah. That way we can observe without waiting for an eclipse.
Right.
Yep. And the reason you can do that in the balloon is because you're above the atmospheric scattering. You can't do that inside the airplane because the light from the photosphere, it doesn't have a direct path to your camera, but it'll scatter off the window and particles in the atmosphere, and it'll find its way in. Yeah.
general question regarding the electromagnetic spectrum and how you use spectroscopes to take that. So how are the optical devices for measuring infrared light different than how it would be for visible?
Oh, that's a good question. They're very, very similar, actually, just between the visible and the infrared. In the X-rays and some of the shorter wavelengths, you get into kind of some differences, but visible and infrared light acts kind of the same, so they're both very reflective off of metal, right? A mirror that works in the visible, as long as it's colored on the front, works just as well in the infrared. The way that we actually spread out the wavelengths, since you asked about spectroscopic in particular, it is using a diffraction grating. Are you familiar with that? If you've ever seen a CD or a DVD, you know, those grooves, if you shine a light on it, you can actually get kind of a rainbow effect. And that's exactly the same effect as what we use. The line spacing, so the groove spacing would be different in the infrared, but very similar to the visible. So the real big difference is this issue with infrared light being heat and having to cool everything. There's not much of a difference between the optics.
In the back.
So I was just wondering, once you measure the magnetic field, I'm wondering how, like, is there a model that you're updating using that information? How is that information used?
Yeah, so we have models of the coronal magnetic field that are based on photospheric magnetic field measurements, which we've been taking since Hale in early part of the last century, and sort of physics-based extrapolations. So the first thing you want to do is really try to add additional constraints on those models. So we would take those models and predict what an observation would see, and then see, does the observation actually, you know, it doesn't agree, so what do I have to do to my model to make it agree? That forward modeling is kind of the easiest way to do this. If you can try to invert things and get sort of piecewise detailed measurements of the magnetic field from the observations, but there you're also bringing in ad hoc information or assumptions about, because the corona has you see light throughout the corona. As when you saw that movie, you know, you have this sense that you're seeing emission. It's optically thin, so light from the nearest part of the plasma and the furthest part of the plasma are both coming to see you. The light from behind doesn't get obscured by the light that's emitted in front. And so when you're measuring a magnetic field in that environment, you're measuring the magnetic kind of some weird average of the magnetic field along your line of sight. So any interpretation of that measurement is going to require modeling. And from my point of view, the easiest way to do that is I make a model, I predict an observation, I look at the observation, they're wrong. I try to see, you know, what set of models are relatively consistent with the observations and get some constraints on it that way. And I think that's kind of how we're going to behave. Now, we have been negligent in mentioning a very large, major piece of instrumentation that's a ground-based telescope called DKIS, the Daniel K. Inouye Solar Telescope on Haleakala in the island of Maui in Hawaii. And that is a 4-meter solar telescope that will look at the surface of the sun, measure magnetic fields. It will measure magnetic fields in the chromosphere, and it also is particularly designed to measure magnetic fields in the corona. And it covers some of the same wavelength regions that we cover. So the AIR-Spec instrument, part of the motivation of the AIR-Spec instrument is looking at these lines at high altitude and comparing, you know, sort of getting a sense as to what the contributions are, what the atmospheric contamination might be for DKIS. So DKIS is going to be coming on, getting first light probably this November, I believe. And so it's designed to measure magnetic fields in the corona. So part of our balloon motivation is, you know, a ground-based instrument looking at the sun with a 4-meter telescope has a relatively small field of view. The balloon instrument will have the global corona and be able to observe it for multiple days, so you don't have the sunrise, sunset. Okay.
We have time for maybe one last question.
what in your backgrounds got you interested in studying the sun in the first place? And if somebody wanted to go on and further your work coming up as a youngster now, what should they be considering for studies or education?
You want to go first?
Sure. Yeah, so I went through this business back when dinosaurs were moving and roaming here. So it was different. But I kind of was interested in solar physics, in the solar aspects of astronomy in college. And so I chose, a graduate school at the University of Colorado that had, multiple options. I was, as Kathy alluded to, kind of on the more modeling theory side of things. I was never very practical in the lab and didn't enjoy, staying up at night and doing observations. I was a terrible astronomer. I actually did observing with a parallax telescope at Wesleyan University, and on glass plates, and and my stars were really always ellipsoidal. It's like this guy is unable to track a freaking telescope. It's like, so I kind of was steered, but the mathematics was made more sense to me. So I kind of, a lot of the physical processes, I understand them really from the MHD equations. It gives me a more grounding in trusting the equations and understanding how things work. So I came to it from the physics background. My work here is science justifications for really cool instruments, right? So there are lots of really cool instruments that I don't build. But but I could understand what I want to do with them and how it puts forward the science, and so that's kind of my niche.
Yeah.
As it were.
I came at it from the exact opposite side. So I had an engineering background, and I've only recently started studying the sun when I came to the CFA about 5 years ago, I guess. So I wanted to build an instrument for my thesis, and originally I was going to build an atmospheric instrument, and then I found out about this project, and it sounded the challenges and also the science itself seemed interesting, but it wasn't what drew me to it originally. It captured my attention more than atmospheric science did, if there are any atmospheric scientists here, once I learned about it. But really what brought me to it was building the instrument and all the difficulties involved in that, and staying up in the lab late, and all the things that you didn't like.
I make a good team.
Yeah. So I guess you asked a question about how to get other people into it. I guess from my perspective, if they're interested in the engineering, I think it would be good. When I was in college, there wasn't in an engineering program. You never really thought that you were going to go out and do anything like this. You were going to go work for a defense contractor or something. So it would just be nice to get the word out that these positions exist, because I would have loved to know that was a possibility.
All right, that's about all the time we have for.
But
There's the video.
There is the video.
Oh, but there's the video.
I'm sorry.
I'm gonna play the actual movie.
Yeah, it does exist. I wasn't actually lying. So this is the early ones. That's the precursor, and then the large one comes up there and blasts stereo away. And you see now the extent of that. Right. This is the solar system, right? So this is 180 degrees across. The sun is here, the Earth is there, Venus, right? Mars, right? So this is massive ejection. Right? Yes, sir.
What did it do to Jupiter?
Did
anybody look at that?
It's not entirely. I don't know.
They're up top.
Yeah. I don't know the magnetism. Yeah, I'm not sure.
So what would have happened if Earth was over there?
Yeah, right. What would have? That's the question. Right. It would have been nasty. Right. It would have been very unpleasant.
We're going into solar minimum, so don't let them scare you. No eruptions for the next couple of years. We're all good. So we're happy to stick around for questions, but we want to get the observing going for the people that are interested in the observing.
Absolutely. So thank you again to Kathy and
We had a project that we were trying to get funded with Russia, and then they invaded the Crimea, and that was just, you know, it's like, actually kind of got cut before that, but it was like, we're really not so sad when, you know,